Right folks, last week we looked at arithmetic, this week we're looking at geometric. So a geometric sequence is something that was introduced in GCSE but not explored very much. It's essentially any sequence where you multiply or divide by something to get to the next term. We say that's having a common ratio. A common ratio is what you multiply by. So for example, we can see 2, 4, 8, 16, we're multiplying by 2. 20, 18, 16.2, we're multiplying by 0.9. What we're multiplying for this next one, we're timesing that by a quarter, or 0.25. You can multiply by negative numbers as well. This one is multiplying by -3, which is why the sign is changing. And this one is just multiplying by -1. It's a little bit funky. Now, the letters that we use are R for what the ratio is, A for the first term, and N for what position we're in. We used A and N with arithmetic sequences as well. So for example, for this one, we'd say R equals 2, and A equals 2, and N is whatever sequence we've got. We'd say R equals 0.9, and A equals 20, etc., etc., etc. So that's the basic idea. So as with arithmetics, the first thing we might want to consider is the nth term. Now if you think about the sequence we've just defined, we're saying that the first term is A, and then we multiply that by our ratio R. So the second term, if that's our first term, will be AR. And our third term, multiplied by R again, will be AR squared. And our fourth term will be AR cubed, and so on. And the idea is that whatever number in the sequence you're at, take away 1 from that, and you get the power that's actually in the question. So we have come up with this general formula for our nth term of A times R to the n minus 1 because of that. Let's see how that works. So we've got here a sequence 4, 12, 36. We can see that that's being times by 3. So the information about that is that A is 4 and R is 3. So UN, our nth term, is A, so 4 times R to the n minus 1 times 3 to the n minus 1. And that's it. That's our nth term. It says that we then want to use that to find the 10th term of the sequence. So that means we're going to use n equals 10, and we're going to substitute it into the formula that we've just come up with. So we can say that our 10th term is equal to 4 times 3, and this time to the power of 9. And that gives us a suitably massive 78,732. Then a slightly more difficult question, and there's two ways of approaching this, so I'll show you both. Find which term is equal to 2 million, and so on. We're saying in this case then that UN is equal to this 2,125,764, and we know what UN is. We know it's 4 times 3 to the n minus 1. So the first step there is going to be to divide by 4. If we do that, we'll get a much less massive 531,441, which is equal to 3 to the power of n minus 1. Now this is where you've got your two options. One way is to take logs of both sides. So if I took a natural log of the left and I took a natural log of the right, and then I could use the power law to take this and put it in front of the logarithm. So I can say n minus 1 lots of ln3 is equal to our ln of 531,441. I can then divide across by the ln3. And we can get that n minus 1 is equal to 12, and so that would tell us that the 13th term is the one that's equal to that. But another way of doing that is just pressing the equals on your calculator, to be honest. If we've worked out that 3 to the n minus 1 is equal to 531,441, well, just type some things in your calculator and see if it's right. If I type in 3 to the power of 9, that's equal to 19,683. That's not quite right. If I increase it a little bit, if I go up to 3 to the power of 11, I get 177,147, so that's not quite right. And through process of elimination, I'll get that 3 to the power of 12 is the number that I want, and so n minus 1 is equal to 12, and so n is equal to 13. Kind of up to you which way you want to go. They both work. Some will be faster in different situations. Okay, let's try and apply the same thing here. We've got a negative value of r here. If we do minus 4.8 over 12, we'll get that the times in here by minus 0.4. or you could put in the fraction if you really want. We want to find the nth term here, so we know that a is equal to 12, we know that r is equal to minus 0.4, and so the nth term, our un, is equal to a times r to the n minus 1. Make sure if you've got a negative ratio that you do put it inside a bracket. It will avoid some issues down the line. It says we want to find the 10th term of this sequence. Once again, that means n equals 10. So we're going to find u10, which is equal to 12 times minus 0.4 to the 9 this time, which is going to give us quite a small number. So we get minus 3.1457 dot 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 times 10 to the minus 3. In standard form, then we're going to have minus 3.15 times 10 to the minus 3. Okay. And then last question, again, I'm going to do this the shortcut way, I think, because the logarithm way probably isn't needed most of the time. We want to find which term is equal to this. So we're saying that 12 times minus 0.4 to the n minus 1 is equal to this 0.049152. What I'm going to do instead is I'm just going to continue the sequence. I'm just going to say, well, if I had 1.92 and times it by minus 0.4, what would I get? I would get minus 0.768. And then after that, I would get 0.3072. And then after that, I would get minus 0.12288. After that, I would get the one I'm actually looking for. There we go. Now we knew this was the third term of our sequence because it was the third term given to us. So we've got our fourth, fifth, sixth, seventh. So it was our seventh term. You can of course do that with the logarithm method. You can of course do it with the hybrid method that we looked on the previous page as well. Just wanted to point it out. Okay, let's get a little bit more awkward and this time use some surd form. We're told about the third term of a geometric sequence and the seventh term of a geometric sequence. So let's write out that information to start with. u3 is equal to 5 and u7 is equal to 20. u3 is equal to ar squared, because its power is 1 less than the term you're in, and this is ar to the 6 is equal to 20. Now have a look at that and think, well, this is a simultaneous equation. How am I going to get rid of one of my things? You might want to rearrange one of them to be a equals or r equals. But there's actually quite a smart thing you can do here, which is to divide one term by the other. So I'm actually going to do ar to the 6 divided by ar squared, and that'll get me 20 over 5. Now if we simplify both sides here, we've got r to the power of 4 here because the a's will cancel out, and we've just got 4 over here. So essentially what we want is the fourth root of 4, which ends up being the square root of 2. So that's our ratio. Now it could be positive or negative, but we are told that the common ratio is positive, so we're going to take that positive root. We probably then want to substitute that back in to work out what a is. So let's substitute it into ar squared. So a times root 2 squared is equal to 5. Root 2 squared is just 2, so a times 2 equals 5. Divide by 2, a is 2.5, or 5 over 2. Still not quite done though, because it wants us to find the 12th term. Now u12, that would be a r to the 11. Again, take 1 away from the power. We know that a is equal to 5 over 2. We know that r is equal to the square root of 2. So let's work this out. We've got 5 over 2 times, so square root of 2 is 2 to the power of a half, so maybe we could use that. So let's say we've got 5 over 2 times 2 to the power of a half times 11, to the power of 11. And then we can use the bracket rule to sort of multiply those powers together and say we've got 5 over 2, and this will be 2 to the 11 over 2. Now, does that make your life any easier? It's still not quite in surd form. Well, it does, in the sense that we can split this up and say that this 2 to the power of 11 over 2, that's 2 to the power of 5 times 2 to the power of a half, because 5 plus a half would give me 11 over 2. If we then think about what we've got here, we've got 5 over 2 times 2 to the power of 5 is 2, 4, 8, 16, 32, and then the square root of 2. Do a little bit more tidying up with the actual fraction, so 5 over 2 times 32 is going to be 80. We'll end up with 80 root 2. Okay, here's another question we can ask, this time a little bit more algebraic. So we've got the first 3 terms of our geometric sequence. We want to find the possible values of x and what the 5th term could possibly be. So again, remember how we could label these. We could say that a, that's our first term, is equal to x minus 3. We could say that ar, which is our second term, is equal to x. And we could say that ar squared is equal to 2x minus 4.5. And we want to try and substitute something into something that will get rid of something. So there's kind of 3 variables here. So what I'm going to do is this. I'm going to find an expression for ar over a, which is going to be x over x minus 3. And that's going to tell me that r is x over x minus 3. And I'm going to do the same thing with ar squared over ar, which will give me 2x minus 4.5 over x. And again, the a's will cancel, one of the r's will cancel, and we'll end up with r equals 2x minus 4.5 over x, which makes sense because r is just what we multiply to get from one term to the other, and we've just divided successive terms by each other. These are therefore the same as each other, so we can get rid of r as well, and we can say, okay, so x lots of x minus 3, or x over x minus 3, is equal to 2x minus 4.5 over x. From there, you've got an equation in one variable, and your general idea would be to expand it. So we'll bring everything up to one side, so we'll times across by the x there, we'll times across by the x minus 3 on the other side. We'll then expand that, so we'll say x squared is equal to, what would that be? 2x squared minus 10.5x plus 13.5, and we can bring the x squared across to make it a 0, so x squared minus 10.5x plus 13.5. Now I don't like that. You could stick that into your calculator straight away, but I'm going to double both sides so that we have something we could maybe factorize. And let's see, we should have 2x and x. We want numbers at times to 27. Yeah, it should be doable. So we can have a minus 9 here and a minus 3 here. That should work. Yep. So our possible values of x are 1.5 and 9. So we've actually got 2 possible things that could work here. Now, we're being told that we need to find a possible 5th term. So, well, let's go with each possibility. Let's start with x equals 1.5. In that case, our numbers would be minus 1.5, then 1.5, then minus 1.5 again. So our sequence here is actually multiplying by minus 1 each time. And if we wanted to work out the 5th term, we could just multiply by minus 1 a couple more times, and we'll end up back to 1.5 and then back to minus 1.5. So in that case, that would tell us that the 5th term is minus 1.5. If, however, we're saying x equals 9, then if we sub them into our sequence, so we sub it into x minus 3, that gives us 6. Sub it into x, that gives us 9. Sub it into 2x minus 4.5, that gives us 13.5. Then we're multiplying by 1.5 each time. And so we could extend that a couple more terms, and we could get that the next 2 are 20.25, and then times it by 1.5 again. We'd get as our 5th term is 30.375. So 2 possible values of x there, 2 possible ways we can get the 5th term as well. Okay, one more to look at. Again, we've got our geometric sequence. This time we can see straight away that a is 4, and we can see that r is 5 because it's just being multiplied by 5. And we're asked, what's the first term to exceed 100 million? Now again, you've got 2 options here. One option is you could work out the nth term. Now the nth term is a r to the n minus 1, so that would be 4 times 5 to the n minus 1. And we want this to be bigger than 100 million. Now we'd first divide by 4, which would get us down to this being bigger than 25 million. And then you could do a logarithms approach. So we could take logs of both sides, and then we could also use the power to bring the n-1 to the front. So we could say n-1 ln5 is equal to ln of 25 million. We could then divide across by that ln5. And we're not dividing by any negatives, so we don't have to think about the inequality sign changing, which is good. And we'll get that this should be bigger than 10.58 for n-1. You can then add the 1, and we can say n is greater than 11.58. And n does have to be a whole number because it's measuring somewhere within the sequence. That would tell us that n is at the very least 12. That's one way. Another way of doing it is to just work it out by timesing by 5 and seeing how long it takes. So let's do that. Okay, I've skipped a bit here, so I've spared you having to watch me work them out. Here we go. It's the 12th one. Gives us exactly the same answer as the left-hand side method. Doesn't really use much in the way of maths. Up to you which one you want to use. Obviously the left-hand side one is going to be more powerful going forward, but if you hate your logarithms, there are ways around this.